This video deals with fluid dynamics, which is essentially fluids that are moving. So the first thing is to define something called the volume flow rate. The symbol for it is Q, and it's V divided by T, where V is the volume of the fluid, and of course T is time. Common units are cubic meters per second, although you could have other units like liters per second. So if you look at this diagram here, you can see that this represents a volume of fluid, and it's equal to this cross-sectional area times the distance. So we can say that Q, which equals the volume divided by time, is equal to this area times this distance divided by time. And of course, distance divided by time is average velocity. So Q can be expressed as area, cross-sectional area, times the average velocity of the fluid. Fluids are not compressible, nor do they bunch up when a fluid flows into a narrow section like you see down here. So the rate of flow must be the same for both this wide section and the narrow section. Or in other words, Q1 must be equal to Q2. And from what we saw in the last slide, that means A1 times the average velocity, V1, is equal to A2, this cross-sectional area, times the average velocity, V2. So that means that as the tube narrows, since A2 here is less than A1, then the velocity of the fluid must increase. So V2 must be greater than V1. So this is called the equation of continuity, and explains why when rivers narrow, the velocity of the water increases. So as the fluid, as it goes from this fat end to the thin end here, the velocity of the fluid is going to increase. Here's a problem that illustrates this, what we were talking about in the previous slide. We've got a nozzle with a radius of 0.25 centimeters attached to a hose with a radius of 0.9 centimeters. The rate of flow through the hose and the nozzle, remember they're going to be the same, is 5 times 10 to the negative 4 cubic meters per second. We want to find the velocity of the fluid, in this case water, in the hose and in the nozzle. Okay, so we can start out by computing this average velocity, which is going to be the Q divided by the area. But we've got to calculate for the hose, we've got to calculate this cross-sectional area. Notice we were given the radius as 0.9 centimeters. So area is pi r squared. Pi is 3.14. The radius in meters is 9 times 10 to the negative 3. Notice we have to take that decimal point, move it over 2 places to the left in order to convert it to meters. So that gives us 9 times 10 to the negative 3, which we square, and that gives us 2.54 times 10 to the negative 4 square meters. So that's the cross-sectional area of the hose. So now we can compute the average velocity. We take that flow rate divided by the cross-sectional area. We get 1.96 meters per second. That's the velocity of the water in the hose. Okay, we move to the nozzle now. Again, we've got to compute the cross-sectional area of the nozzle. So that, again, that's pi r squared. Here, this is 0.25 centimeters. We convert that to meters. 2.5 times 10 to the negative 3. We square that. Gives us cross-sectional area of 1.96 times 10 to the negative 5 square meters. Now we can compute the average velocity. We divide the flow rate by that area, and we get 25.5 meters per second. So you can see here that the water moves faster 25.5 meters per second as opposed to 1.9 meters per second when the water goes from the wide cross-sectional area of the hose to the narrow cross-sectional area of the nozzle. Bernoulli's principle and equation. Okay, first Bernoulli's principle. So when the velocity of the fluid is high, the pressure is low, and when the velocity of the fluid is low, the pressure is high. So here's a good example of this. If you just take a small strip of paper, for example, loose leaf paper, and you blow across the top surface of it, the paper is going to curl upward like this. And it does so because of the lower pressure on the top where you've blown across it and the velocity of the fluid is high, and the pressure on the bottom is going to be higher, so it makes it curl up. We'll talk more about that in a bit. Okay, this is Bernoulli's equation, and it says P1 times 1/2 density of the liquid times V1 squared plus the density of the liquid times G times H1 equals pressure, any other pressure, plus 1/2 density V2 squared plus density GH2. Okay, now this equation may look a bit complicated, but if you just look back over here, which is a restatement of the conservation of energy, if you take each one of these terms and divide it by volume, you're going to get this equation up here. So, for example, 1/2 mv squared, mass per unit volume, is density. And we get mgh, we divide that by volume, and we get, again, density times g times h. The one that might not be quite so obvious is this work term, W1, but we know that pressure is force per unit area. We defined that earlier. And if we multiply both sides, both numerator and denominator here, by x, what we get is work, force times x, displacement is work, and area times x is volume. So essentially then, if you divide work by volume, that's equal to pressure, and so that's how we get that term. And of course, the same thing applies to each one of these terms. Bernoulli's equation for static fluids. So if a fluid is static, then that means that it's not moving and its velocity is zero. So here is Bernoulli's full equation that we saw in the previous slide here. And if the fluid is static, then that's going to mean its velocity here is zero and its velocity here is zero, and that's going to leave us with this. We can simplify this further by assuming or assigning H2 to be equal to 0. This can be just an arbitrary point. So we're making that 0, and that makes the fluid, that makes H1 lower than H2. And so therefore, when we have this equation, what this tells us is that P2 is equal to P1 plus the density times G times H1, which is exactly what we have seen before in the previous video, which said that as the depth of the liquid increases, the pressure increases. Okay, so it's telling us reducing down to something that we've seen before. Okay, now Bernoulli's principle, which we saw in the previous slide, we can demonstrate that by looking at Bernoulli's equation at constant depth. Okay, so here's Bernoulli's equation. Constant depth means H1 and H2 are the same. And of course, G and density would be the same. We're talking about the same fluid. So therefore, these two terms would add out. And so that leaves us with this, which tells us that the pressure plus the kinetic energy of the fluid is equal to any other pressure and kinetic energy of the fluid. So if you have a fluid and it goes into a narrow opening like we had seen before, then that means that the pressure is going to increase, but the kinetic energy and the velocity, therefore, is going to decrease. So this is what we had seen before as well. Okay, so here's a problem. In a previous problem, we showed that the speed of water in a hose increased from 1.96 meters per second to 25.5 meters per second as it entered the nozzle. We want to compute the pressure in the hose if the absolute pressure in the nozzle is 1.01 times 10 to the fifth newtons per square meter. Notice that's air pressure. We're assuming frictionless and level water flow. So level, of course, means that we're not, the hose is not increasing and decreasing in height. So we can use this abbreviated form of Bernoulli's theorem for constant height. Okay, so we want to solve for the pressure in the hose. So that's P1. And so P1 is going to be equal to P2 plus 1/2 times density times V2 squared minus 1/2 the density times V1 squared. Now, before we plug the numbers in, it'll make life a little bit easier if we factor out the 1/2 and the rho here, the density of water, which is constant here and here. So we have P2 plus 1/2 rho times V2 squared minus V1 squared. Okay, so here is P2, is the pressure in the nozzle, plus 1/2. Here is the density of water, 1 times 10 to the third kilograms per cubic meter, times 25.5 squared. That's the velocity in the nozzle, minus 1.96, the velocity in the hose, and those two terms are squared. So we work through the numbers, and we end up with 4.24 times 10 to the fifth newtons per square meter. So this is the pressure in the hose. Notice that the pressure in the hose is bigger than the pressure in the nozzle, and of course that's because the velocity of the water in the hose was lower than the velocity of water in the nozzle. So here are a couple of applications of Bernoulli's theorem. This one over here is called an atomizer or perfume sprayer. And the way it works is you have a little bulb here and you spray or you push a column of air across the top of this tube, and the air has a high velocity, and the high velocity means a lower pressure, and the higher pressure in here forces the liquid up and out here. Okay, another example here is an airplane wing, and you can see that because of the shape of the wing here, the air has got to move faster across the top than it does across the bottom, and that reduces the pressure on the top, and that gives an upward lift here to the wing.